Hello, everyone. Welcome. Hope you had a great Thanksgiving weekend. Everyone's doing well. This is our last week of class, and today is actually our last lecture. So, wow, we did it. So we have a couple more exams to go, but we made it through the semester. So that's kind of nice, right? Um, I just I really am grateful for all of you and your patience with me and with this way of teaching. It's not ideal, but you guys have been amazing. You've been diligent. You've stayed up with a pretty intense workload and with a lot of assignments, right, to keep you going. And I just appreciate it. You guys have been great. So you've made this a lot easier for me. And gosh, I wish I could meet you all in person, but we'll see. And I'm sure I'll see many of you next semester in Chem 156. A couple of you have been asking about the book for that class. It's the same book. You don't have to buy anything new. You can just keep using the same thing you've been using all semester, which is really nice. So let's see, a couple of quick things. Exam 4, I decided to move it to Thursday because there's a lot going on Wednesday with the lab and the pre-lab lecture and all of that. So the exam is now going to be on Thursday, December 3rd, and you can take it anytime between 2 and midnight. It only covers 2 chapters, so it's a little bit of a shorter exam than the last ones have been. You have 60 minutes to complete it, okay? So that is on Thursday. There's a pretest, of course, that's due on Thursday as well. And I believe it's due at 2 p.m. on Thursday. All right, so make sure you get that done. There's still one more problem set. It's a written problem set. I sent that to you already. You should try to get that done probably by tomorrow or Wednesday so you have enough time, right, to study for the exam, okay? The final exam is going to be chapters 1 through 11, and that's going to be on Monday, December 7th from 2 to midnight. That's going to be a 120-minute exam, all right? That's going to be a little longer than the other exams, probably be about 60 questions or so, okay? So make sure you're ready for that. I'll have 2 additional Zoom sessions after this, but they're just going to be help sessions and question and answer sessions. So one is going to be on Wednesday from 2 to 3 in normal class time. I'll be available to answer any last minute questions you have on the exam. And then I'll have another one on Monday from 1 to 2 to answer any last minute questions you might have about the final, okay? If you look at Mastering Chemistry, you'll find that I've reassigned the pretests for the 4 exams that you've had to date. You can go on there and redo those. They're not for credit, so you don't have to, you won't lose points, you won't gain points, but they're just for you to practice for the final. All right. So those are all of my announcements. We have a little bit of material still to cover today. I'm going to rely a lot on the videos that you saw with Mastering before class. So I hope you've all seen those. If not, make sure you watch those quickly right after class to get up to speed on the remaining material, okay? I will review that, of course, in today's class, and then we'll do our usual review for the exam. Any questions before I get going? Do you have a pre-lab assignment? Oh, that's a good question. I don't, shoot, it's in my email that I sent out summarizes all that. And at the moment, I can't remember. So if you can just look at the email that I sent out, it'll answer that question. Oh yeah, that's right. It's a paper lab, right? So I don't think there's a pre-lab assignment. That's right. Whew. Any other questions? That paper lab is useful because it goes through a lot of the stuff we've been covering and will also help you on the exam. So it'd be worth, make sure you try to do that lab as soon as you can. It'll be helpful. Okay, let's go ahead and finish chapter 11. So if you remember last time, we started talking about valence bond theory, right? And remember, a chemical bond in valence bond theory is the overlap between half-filled orbitals, right? And those orbitals could be the normal unhybridized orbitals that we know and love, or they could be hybrid orbitals, right? And we looked and we were starting to look at the different possible hybrid orbital combinations. We saw that one of those, let me just start this slideshow. We saw that one of those is the sp3 hybrids, where you add together an s and 3 p orbitals, right? And the sp3 hybrids look like this. They're tetrahedral, okay? We saw that a hybrid orbital has has a bigger lobe on one side, which means it can overlap better, which is why hybridization happens, right? And remember last time we decided that we're only going to hybridize interior atoms, not terminal atoms. Okay, so terminal atoms are going to bond through their normal SPD orbitals, right? Interior atoms, ones that are bonded to multiple atoms, are always going to bond through the hybrid orbitals. Okay, and I'll show you in a minute how to decide on which hybridization to choose. Okay, but let's go through the hybridizations really briefly. Again, you've seen this in the video, so hopefully none of this is new. sp2, it's combining one s and 2 p orbitals. This is the energy diagram. You get 3 sp2 hybrids and an unhybridized p. All right, these orbitals look like this. They're very similar to the sp3 hybrids, except there's only 3 of them, and they are trigonal planar in geometry. Okay. Now, the reason, let me do an example of a molecule that bonds via sp2 hybridization. All right. And I still haven't told you how to decide on hybridization, so just hang tight for a minute. But this molecule is formaldehyde, okay? And what I want you to be able to do for valence bond theory is to draw what I call a hybridization and bonding scheme, all right? And that's where you draw the molecule and you draw an image kind of like this that shows all the orbitals that are overlapping and all the bonds labeled, okay? So the way you would do this is you'd say, okay, you look at this carbon and you say, there's your central atom. Then you decide on the hybridization for the central atom. In this case, it's going to be sp2, all right? And I'll tell you how I decided that in just a minute, but it's going to be sp2. So you're going to draw the central atom with its sp2 orbitals. I'm going to draw one in the plane of the board, one going into the board, one coming out of the board like that, okay? And then whenever you have sp2 hybridization, you also have this leftover unhybridized p orbital. And that unhybridized p orbital can also be involved in bonding. All right, it can form what are called pi bonds. All right, and so we'll see that here in a minute. So I'm going to draw in that unhybridized p orbital right here. Okay, carbon has 4 electrons. It's going to be 1 electron in each of these 4 orbitals. And that central atom is going to look like that. Okay, the hydrogens are terminal, so they're just going to bond through their unhybridized 1s orbitals. So if we label this bond, it's going to be sigma hydrogen 1s overlapping with carbon sp2, right? This tells you the hybridization, the kind of orbital that's bonding on the carbon. It's an sp2 hybrid. All right. Then now notice you can sort of use the Lewis structure as a guide here as you work, right? Here's the carbon, here's the 2 hydrogens. And now I got this oxygen. So the oxygen, again, is terminal. So it's unhybridized, right? And what does it have to bond with? It has 2 p orbitals that each have 1 electron in them, right? If you look at the orbital diagram for oxygen, it shows you those 2 half-filled p orbitals. So here's another bond, right? That one is sigma carbon sp2 overlapping with oxygen p, right? Now there's still one more bond to form, because notice there's always going to be a correspondence between the Lewis structure and the valence bond model. All right, here you have 1, 2, 3, 4 bonds. 1, 2, 3, right? The 4th bond is a different kind of bond called a pi bond. And it's the overlap between these 2 side-by-side half-filled p orbitals. And so we label that one, we call it pi. Sigma bonds are typically like this kind of overlap, right? Where it's head-to-head. That's sigma. Pi bonds are going to be this kind of overlap. side to side. That's pi. All right, so that's the difference between a sigma bond and a pi bond. So this is a pi bond, and it's between the carbon p orbital and the oxygen p orbital. All right, and this whole thing right here is a hybridization and bonding scheme for this molecule. All right, and that's kind of what I want you to be able to do, and that's what you have to do on your homework. Of course, on the exam, it's going to be multiple choice, so you won't have to write this out exactly, but I'll ask you questions that will require you to sort of know how to do this. Okay. You can see kind of a better drawing of the same thing right here, right? Showing all the bonds. Notice what valence bond, notice one thing that valence bond theory does for us here is it shows us that a double bond is not just two single bonds that are identical, like it does in the, like it looks in the Lewis structure, right? A double bond is a sigma bond here in the middle and then a pi bond above and below the plane. A pi bond is different than a sigma bond because a pi bond can't rotate, right? A sigma bond, this oxygen atom can rotate and not break that pi bond. Sorry, that sigma bond, but it cannot rotate and not break the pi bond. All right. Single bonds are always one sigma, one pi. Sorry, double bonds are always one sigma, one pi. Triple bonds are always one sigma and two pi. All right, and I'll show you one of those in a minute. All right, so here's the molecule. Here's the Lewis structure. Here's the valence bond model description. All right, notice again, this oxygen can't spin without breaking that bond. Again, sigma bond end to end overlap like this. Pi bond side to side overlap like this. Okay. Now, this becomes super important in some sorts of molecules. Like for example, if I look at this molecule, which has two carbon atoms and two chlorine atoms, it only has a single bond between the carbon atoms. Here's a sigma bond right here. Each carbon atom is sp3 hybridized, and there's a single bond. This is free to rotate, right? Now, notice if I have a pi bond between two carbon atoms, then I have a sigma and a pi, right? That makes up the double bond. And this is not free to rotate. All right. That means that this molecule with a single bond, free rotation. All right. But this molecule with a double bond, not free rotation. So there's a difference between this and this. This can't rotate into that without breaking that double bond. So you see, valence bond theory has given us insight into the nature of a double bond. It's showing us that it's one sigma and one pi.
I have a question.
Yeah.
What does the 1,2 next to the dichloroethylene?
You know what? That's just the way it's named. You don't have to really worry about that for right now. Right now, I just want you to understand that this bond is free to rotate. This bond is not.
Mm.
But that's part of the nomenclature. Okay. Another hybridization that could happen is called sp, which is just one s and one p. It results in two sp hybrid orbitals, and you have two unhybridized p orbitals left over. So that they look like this. It's a linear geometry for sp hybridization. And a molecule that has that is this molecule where you have a triple bond between the carbon atoms. All right. Notice that in the triple bond, each carbon is sp hybridized. So here's the carbon, here's the sp hybrid, here's the other carbon sp hybrid. You form your sigma bond between those two hybrids, right? But then you form your pi bonds between the carbon unhybridized p orbitals. And notice now that I'm forming not just one pi bond, but two. One up and down, and one in and out of the paper. All right. All right. A couple other hybridizations that could happen if we involve the d orbitals. So we could have sp3d, and that results in 5 orbitals that look like this, 5 hybrids that look like this. Here's a molecule that has it. These are the 5 hybrids right here, 1, 2, 3, 4, 5. And these are the hybrid orbitals overlapping with the fluorine p orbitals. All right. You could also have sp3d2, which is 1s, 3p, and 3d. That results in 6 hybrid orbitals, and they look like this. Here's a molecule that has that. Sulfur sp3d overlapping with fluorine p. Okay. Now, I see a couple questions. I'll get to those questions in a minute. Let me see if you can answer this question, though. I want to see where you are. Go ahead and try this for me. So I'll give you a hint. Remember that a pi bond is an overlap between unhybridized p orbitals, right? So another way to ask this question is, which one of these has at least one unhybridized p orbital? Okay, about 10 more seconds. Okay, the right answer was B. And you see that that's sp2, right? So remember what these numbers mean. That means you combine 1s and 2 p orbitals, right? That means that there is 1 p orbital left over, and that p orbital can then participate in the pi bond. All right, remember, you got to have leftover. Notice here you've used all the p orbitals in the hybridization. Here you've used all the p orbitals in the hybridization. So there's no leftover p orbitals, right? You got to have a leftover p orbital in order to form a pi bond. Okay, let me take a couple questions and then we'll move on. Abe.
Could you do an example on CO2?
Yes, I will. I'm gonna do a couple of examples here. I can do CO2. Absolutely. Hang on for a second, okay? I will.
Okay.
Megan.
Do you mind explaining the notation where you have like this in the drawing you did on the side, where you have the sigma, you have the H1sc sp2.
Like this?
Yeah.
Yeah, so that notation is the type of bond, sigma or pi, right? Sigma is like this, pi is like this. Then it's the atom, in this case hydrogen, and then the orbital on the atom where the electron, where the single electron is, it's doing the overlapping. In that case, it's 1s, right? And then bonded to carbon, and then the orbital on the carbon that's doing the bonding. In this case, this orbital right here is an sp2. Does that make sense? So when we look at this one, for example, it's pi because it's side to side. It's carbon, and that's a p orbital overlapping with an oxygen p orbital. Right, so that's what it does. Okay?
Okay, thank you.
Great. All right, so how do you do this? How do you decide what hybridization to choose? Again, normally, if you're really doing valence bond theory, you'd have a computer calculate what hybridization gives you the lowest energy, but we're not going to do that. What we're going to do is we're going to say interior atoms always hybridized, terminal atoms never hybridized, all right? And you decide the hybridization of the interior atom from the Lewis structure for the molecule. So we're going to mix our models here a little bit because the Lewis structure is going to be able to predict for us what the correct hybridization is. And what you're going to look at, you're going to draw the Lewis structure, and then you're going to look at the electron geometry. And the electron geometry based on the Lewis structure will tell you what hybridization to choose for that interior atom. All right. So if it's linear, it's sp. If it's trigonal planar, it's sp2. If it's tetrahedral, it's sp3. If it's trigonal bipyramidal, it's sp3d. And if it's octahedral, it's sp3d2. Okay. So let's just pick the hybridization for each of these interior atoms, right? How many electron groups here?
4.
4. So if there's 4 electron groups, then the electron geometry is tetrahedral. So the hybridization would be what?
SP3.
sp3. Okay. It's just that easy, right? How many electron groups here?
4 again.
5.
4 again. So it's sp3 again, right? Terminal atoms never hybridized, right? So hydrogen, what's it bonding on hydrogen? It's just the 1s orbital, right? The 1s orbital. This central boron has 3 electron groups. So what's the hybridization there?
SP2.
sp2, exactly right. Right? So you just count the electron groups and that gives you the hybridization, right? So let's do CO2. All right. So we go, okay, the first thing to do whenever you're applying valence bond theory is you first draw the Lewis structure, no matter what, because that's what's going to guide you. All right. So there's our Lewis structure. Okay. Terminal atoms are going to be not hybridized, right? So that means the oxygen is going to be binding through its p orbitals, right? Because if you look at the electron configuration for oxygen, it has 2 unpaired electrons in p orbitals, right? So we know the oxygen is going to be binding through the p orbitals. The carbon, we need to decide the hybridization. How many electron groups in carbon dioxide?
2.
4.
That's not an electron. That's just a dot. 2 electron groups, right? So what's the hybridization?
Linear or SP.
P.
sp. Okay, it's sp. All right. So we're going to draw that carbon. We're going to draw the sp hybrids. We're going to remember that whenever you have sp hybridization, you have some leftover p orbitals, right? Let's go back to sp hybridization here. sp hybridization, you get your 2 sp hybrids. And what do you have left over?
The 2 p orbitals.
The 2 unhybridized p orbitals, one going up and down and one going in and out. Okay, so you have these 4 orbitals. Each one has 1 electron. 1, 2, 3, 4. Remember that these sp hybrids, that these p orbitals, that counts as 1 entire orbital, right? This is 1 entire orbital. The hybrids, though, that's 1 orbital, that's 1 orbital, right? The back lobes on these hybrid orbitals are really tiny. You can't even, I'm not even drawing them here, okay? So there are your 4 half-filled orbitals are going to be making these 4 bonds, right? The oxygen atom, again, it's going to bond through its p orbitals. Each of those has 1 electron, right? And the other oxygen over here, same thing, except I'm going to draw it going in and out. All right. So here you have sigma bond, right? So let's label that. That's going to be carbon, sigma, carbon. And then that orbital is an sp hybrid orbital bonding with an oxygen p orbital, right? This is going to be exactly the same thing, all right? But notice you have 2 double bonds, so I got to form those double bonds. 1 double bond is the overlap between these 2 orbitals, right? That's going to be pi, carbon, p, overlapping with oxygen p. And then the second double bond is going to be in front of and behind the board, right? So 1 there and 1 there. And that's also pi, carbon, p, oxygen, p. Like that. Abe, you have a question?
Yeah. So there's 2 sp sp hybrid orbitals, right?
Yeah.
So one goes each lobe as an orbital.
Sorry, you're breaking up. I couldn't
Huh?
quite hear that last part. There are two p orbitals, unhybridized, one up and down, one in and out. And what was your question?
And then where are the two sp orbitals?
The sp hybrids are here and here.
Okay, so okay, and then next question is why does the oxygen only have pretty much? I guess I'm thinking about two p orbitals.
Because remember that terminal atoms are never hybridized. So if you look at the electron configuration for oxygen, right? Its outer electron configuration is 2s2, 2p4, right? So this orbital is full, and in terms of the p orbitals, you have p. You have 1, 2,
Yeah.
3, 4. So you have your two p orbitals here, which are this one and this one.
Got it. But
Got it?
wouldn't those be? Wait. Sorry. Wait. So wouldn't those be considered half-filled p orbitals, and you would just make them into like one lobe each?
No. This is one p orbital. This is one p orbital. Remember, p orbitals always have two lobes. Okay, it's not hybridized.
I guess I'm just thinking about in the sense. Okay. Okay, I think I got it. Thank you.
Okay, awesome. All right, let's see. All right, let's see if you can answer this question. I'm going to draw the Lewis structure for you for XEF2 because that's the first thing you got to do in order to be able to answer this question, right? So remember, xenon has 8 valence electrons plus 2 times 7, that's 14, plus 8 is 22, right? 14, yeah, 22. So you go xenon, and then you have fluorine, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 electrons. We've used 16 so far. So it's 17, 18, 19, 20, 21, 22. There's your Lewis structure for xenon difluoride. And the question is, what's the hybridization? Okay. Remember this table here, right? Look up the number of electron groups, and that's going to tell you the hybridization. Oops. Let me launch the poll. Okay, go ahead and try to answer that. Okay, try to answer the next 10 or 15 seconds or so. Okay, the right answer was D, and virtually all of you got that. So nice work. Awesome. Okay. And again, the way you do that is you count the electron groups, 1, 2, 3, 4, 5, right? And then you go to this little table, 5 electron groups, sp3d. Okay. And the sp3d hybrids look like that. All right. Let's do another example that has that kind of hybridization. Here's the Lewis structure for bromine trifluoride. All right. And you see the bromine and the 3 fluorine. So you count the electron groups, 1, 2, 3, 4, 5. So it's sp3d hybridization, just like the one we just did, right? So what you do is you draw the bromine. You have to remember that the sp3d hybrids, right, look like this. They have a trigonal bipyramidal geometry. 1, 2, 3, 4, 5. Each one of them half filled. And what's bonding on the fluorine atom? The fluorine atom is terminal, so it's not hybridized. The only half-filled orbital that exists on the fluorine is a p orbital. So I've drawn the p orbital on the fluorine overlapping with sp3d orbital on the bromine, right? Notice that the two lone pairs here, right, are in these sp3d hybridized orbitals as well, right? So 3 of them are half-filled, and they're forming the bonds, and the other 2 are completely filled, so they can't bond. The notation here would be sigma, bromine sp3d overlapping with fluorine p in every case, right, for all 3 bonds. All right, let's try this one. There's the Lewis structure. What kind of bonding will happen? What kind of orbitals are going to be bonding for the nitrogen? Well, how many electron groups? 3. So what kind of bonding happens with 3 electron groups? What kind of hybridization?
SP2.
sp2, exactly right. So I'm going to draw my nitrogen with sp2 hybrids. 1 there, 1 there, 1 there. This one's going into the board. This one's coming out, right? Whenever I have sp2 hybridization, I always have a leftover p. So I'm going to draw that one as well, right? There's my leftover p, right? Nitrogen has 5 valence electrons, right? So it's going to be 1, 2, 3, and then this is going to have 2 electrons, right? Because I see that there's an electron pair here that's not forming a bond. That corresponds to that electron pair right there. Okay. So then on the one side, it's bonding to chlorine. So I'm going to draw the chlorine here. Chlorine bonds through its p orbital. So that's going to be sigma, chlorine, p overlapping with nitrogen, what?
SP2.
sp2, right? Just like we decided it was sp2 hybridized. Very good. All right. Then, so that's the bond with the chlorine. Now we got to build this bond with the oxygen. Notice it's a double bond. A double bond is always going to be 1 sigma, 1 pi. All right. So here's my oxygen atom. It has 2 half-filled p orbitals. One of them is going to form a sigma bond. So that's going to be that's going to be sigma nitrogen p orbital. Sorry, not p. Sigma nitrogen sp orbital overlapping with oxygen p. All right, and then we have our pi bond, pi, nitrogen p, oxygen p. Notice pi bonds are always p orbitals overlapping side by side. Okay, they're always going to be that way. Taylor.
I just noticed the pattern. I don't know if this is like a safe bet, but can you basically look at like, okay, I have 5 electron groups and then just count one s p 2, just like it always goes in that stair fashion.
Exactly right. That's
Okay.
totally right. Yep.
Okay, cool. Thank you.
Yep. Okay. How about you try this one? Let's draw the Lewis structure first. So you have the Lewis structure, SF4, right? So you have sulfur and 4 fluorine atoms, right? Total number of electrons is 6 for the sulfur, plus 4 times 7 is 28, 34. Right, so you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, 24, 25, 26, 27, 28, 29, 30, 31, 32. Right, so this has 32 so far, but you got to use 34. So you expand the octet, and there's your Lewis structure. All right, now see if you can answer this question.
What defines a bond as a sigma bond again?
Pardon me?
What defines a bond as a sigma bond? Where the
It says, yeah, which orbitals overlap to form the sigma bond between sulfur and fluorine in this molecule? So I'm asking,
Okay.
what kind of orbitals are overlapping to form this bond? Yeah. Okay, try to answer the next 10 seconds or so. Okay, awesome. Most of you are getting this, so that's good. It's D, right? No. That's wrong. It's not D. It is. It is A. All right, my PowerPoint is wrong. It should be A. sp3d of sulfur and 2p on the fluorine, right? And it's 2p, not 3p. If a few of you put 3p here, you know that it's 2p because fluorine is in period 2, right? So the orbitals that are being filled here on the fluorine, the half-filled orbital is a 2p orbital, all right? And then you look at the sulfur and you go 1, 2, 3, 4, 5 electron groups, right? So it's sp3d overlapping with 2p on fluorine, okay? Nice work. Okay, we will, that answer's wrong. Okay, great. So that's valence bond theory, all right? I have 20 minutes for the last bonding theory, and then we're going to do 20 minutes of review. Okay, so I apologize, the time is a little quick, but this last theory we're not going to get into in too much depth. It's called molecular orbital theory. It's the third of our bonding theories, right? Remember, the first model we looked at was the Lewis model. What's a chemical bond, the Lewis model?
Sharing electrons through bonds.
Shared electron pair, right? A shared electron pair is a chemical bond in the Lewis model. Then we went to the valence bond model, right? What's a chemical bond in the valence bond model?
Overlap of orbitals.
Overlap of half-filled atomic orbitals. And those could be the standard sp orbitals that we know and love, or they could be hybrid orbitals, right? And now we're going to go to molecular orbital theory. And molecular orbital theory, like I said, we're not going to get into too much depth, but basically what molecular orbital theory says is that instead of using atomic orbitals for bonding, what really happens is that the molecule itself has its own orbitals that are a function of the molecule. So in molecular orbital theory, you forget about atomic orbitals altogether and you say, okay, let's solve the Schrodinger equation for the molecule as a whole and look at its orbitals, right? The orbitals that come out of solving the Schrodinger equation for the molecule. So for example, when you solve the Schrodinger equation for H2O, these are the orbitals you get. Notice they look nothing like atomic orbitals that we're used to. They are completely different. They are molecular orbitals. They're orbitals that belong to the whole molecule, right? So the lowest energy orbital looks like this, and it can hold 2 electrons just like any orbital can. But notice that those 2 electrons are spread out over the entire molecule, all right? Here's the next one, is the next highest one in energy is this one, which looks like this. It has a node right there, a little bit reminiscent of a p orbital, right? But not a p orbital because, again, the density is spread out over the whole molecule, all right? And these are the orbitals you get as you go up, all right? And that's for H2O. Now, we're not going to have to worry about H2O because these come from doing calculations that require computer simulations and things like that, which we're not going to be doing. But I just wanted to show you that molecular orbital theory is completely different. It says, hey, Let's forget about atomic orbitals and calculate molecular orbitals, the orbitals of the molecule as a whole. So what we want to do is just be able to apply molecular orbital theory to first and second period diatomic molecules. So we got to ask ourselves, right? This is not a first or second period diatomic molecule. We're not going to worry about this, but I just wanted to show you these are the molecular orbitals for H2O. So the question is, what do the molecular orbitals look like for the first and second period diatomic molecules? All right. And they look like this, okay? For hydrogen, if I have a hydrogen atom, we know that the electron is in a 1s orbital, right? If I have another hydrogen atom, we know that it has an electron in a 1s orbital. In the hydrogen molecule, there are two molecular orbitals, a lower energy one and a higher energy one, all right? What do they look like? They look like, I guess I'm gonna have to draw them for you here real quick, sorry. This lower energy one is called sigma 1s. And if these are the two nuclei, the molecular orbital looks like that. All right. And then you have the sigma 1s star. And if these are the two nuclei, the molecular orbital looks like this. And it has a node right there in the middle. All right. This orbital is lower in energy than the corresponding atomic orbitals. And for that reason, it's what we call a bonding orbital. Bonding orbitals tend to have electron density between the two nuclei. This is higher energy than the two atomic orbitals, and therefore we call that an anti-bonding orbital. Anti-bonding orbitals tend to have a node between the two nuclei. All right? So for H2, notice that the electrons can lower their energy in the molecule compared to the individual atoms. All right, so we're going to define something called bond order, which is equal to the number of electrons in bonding molecular orbitals minus the number of electrons in antibonding molecular orbitals, all divided by 2. All right. The bond order in this case, you'd say, aha, I have 2 in bonding, 0 in antibonding. So 2 minus 0 divided by 2 is equal to 1. So we say that H2 would have a bond order of 1. All right. Positive bond order. A positive bond order means that the electrons can lower their energy by forming the molecule. All right. So positive bond order, lower energy, molecule forms. All right. A molecule form. Anytime you have a positive bond order, that tells you that the molecule will form. Let's compare that to He2. Right. So He2. Each hydrogen atom, each helium atom has 2 electrons, right? The molecular orbitals are the same as they are for hydrogen 2, right? You have a bonding, sigma bonding, and sigma anti-bonding molecular orbital. But now you have to distribute all 4 of these electrons into those orbitals, right? So now the bond order, instead of being 1, right? The bond order for He2 equals 2 minus 2 over 2, which is equal to 0. That tells you that a molecule doesn't form, right? So He2 does not occur. All right, so these are the molecular orbitals for the valence electrons of the group of the period 1 elements, right? So the period 1 elements, right, are just hydrogen and helium. All right. And if you want to do, if you did ions, you just adjust the number of electrons. So for example, here's the He2 plus ion, right? So again, same 2 molecular orbitals, sigma 1s star. But now, because it's an He plus ion, right? He2 plus ion, you only have 3 electrons, right? So 2 go down here, 1 goes up here, right? We fill these just like we would fill any set of orbitals, right? From lowest energy to highest energy. Follow Hund's rule and all that kind of thing, right? So So we'd have, in that case, the bond order would equal what? 2 in bonding minus 1 in antibonding divided by 2 is 1/2. Okay, so the bond order is 1/2. Again, any positive bond order means that you form a bond. And in fact, the He2 plus ion does exist. Okay. All right. So those are these elements. The ones I want you to be able to predict bond order and draw diagrams like this for period 1 diatomics and period 2 diatomics, right? So of course, the next question is, well, what do the orbitals look like for the period 2 diatomics? All right. And what I'm showing you here are only the valence orbitals, right? So you only put the valence electrons in, right? So for hydrogen and helium, of course, that's easy. But the valence electrons, like for lithium, you'd have 1, for beryllium, 2 valence electrons, and so on. Okay. So here's what the energy ordering looks like. All right. For B2, C2, and N2, you got what it's called the sigma 2s and the sigma 2s star. And then you have the pi 2p, sigma 2p, pi 2p star, and sigma 2p star. Anything with a star is antibonding. So for example, let's draw a molecular orbital theory diagram for C2 and predict the bond order. Okay. We'd say, all right, the orbitals are these. You got sigma 2s, sigma 2s star, pi 2p. Remember, this is just the energy ordering of these orbitals, right? Sigma 2p, pi 2p star, and sigma 2p star. Remember, these stars tell you that these are what?
Antibonding.
Antibonding, right? So then you just say, okay, how many valence electrons do I have? Each carbon atom has 4, right? So C2 would have how many?
8.
8. So I have 8 electrons to distribute. So I just put them in the, like I would be filling any other orbitals, right? From lowest energy to highest energy, right? So I'd go 1, 2, then go to the next highest energy one, 3, 4. Now, these have the same energy, right? These are degenerate, right? How do I fill degenerate orbitals? Same as I would for atoms. Do I put 2 and 2, or do I put 1, 1, and then pair them?
1, 1, and then pair.
Exactly. So I go 1, 2, 3, 4, 5, 6, 7, 8. Right? So there we go. This is what I want you to be able to do. This is all you need to do for valence bond theory. Draw a diagram like this and then predict 2 things. I want you to be able to predict the bond order and then predict whether it's diamagnetic or paramagnetic. Remember what those definitions are. Paramagnetic means that it has unpaired electrons. Okay, diamagnetic means it doesn't have any unpaired electrons. All right, so first of all, what's the bond order for this? How many electrons in bonding molecular orbitals? How many electrons in bonding molecular orbitals?
6.
6, yep. 1, 2, that's antibonding. 3, 4, 5, 6. Okay, so it's 6 minus how many in antibonding molecular orbitals?
2.
2 right there. 6 minus 2 divided by 2. So that's 4 divided by 2 is 2. So is this thing going to form? Yes. Okay. Is it going to be diamagnetic or paramagnetic?
Diamagnetic.
Diamagnetic. Right? That's it. That's all I want you to be able to do. All right? Does that make sense? For these 3 diatomics over here on the right side of the period 2, the energy ordering is slightly different. These 2 change places. Okay? So that the sigma is there and the pi is there. So let's do O2, right? So for O2, I got to remember, again, you got to use the right energy ordering. So I have sigma 2s, sigma 2s star, sigma 2p, pi 2p, pi 2p star, and sigma 2p star. Again, my antibonding orbitals are this one, and this one, right? Those are all antibonding as they're indicated by the stars. Okay. How many electrons, how many total valence electrons for O2?
12.
12, right? So I got 12 electrons for O2. So again, I just fill them up. 1, 2, 3, 4, 5, 6, 7. Where does my eighth one go? On the left or the right?
Right.
Right. 8, 9, 10, 11, 12. Right? So what's my bond order here? How many electrons in bonding molecular orbitals?
8.
8. Yep, 8. How many in antibonding?
2. Oh, 4.
4.
4 divided by 2. That's 4 over 2. Bond order again is 2, right? Just like C2. All right. What about dia or para? Magnetic. Paramagnetic, right? Because it has unpaired electrons. Okay. In fact, if you look at the Lewis structure for so this is the molecular orbital picture of O2, right? Let's look at the Lewis structure of O2. Does the Lewis structure show any unpaired electrons?
Yes. Wait,
Where?
no. Wait.
These look like they're all paired up, right?
Yeah.
So this is MO theory right here. This is Lewis theory right here. And then valence bond theory. How would we do O2 with valence bond theory? Well, these are both terminal, so they would bond through their unhybridized p orbitals, and it's a double bond, right? So I would have one electron there, electron there, electron there, electron there. These pair up and form the pi bond. These pair up and form the sigma bond, right? So here's my pi, oxygen P, oxygen P. Here's my sigma. It would be oxygen P, oxygen P. All right. So there are my three models all side by side, right? Here is my Lewis model. Here's my valence bond theory. Here's molecular orbital theory. Notice, Lewis model, no unpaired electrons. Valence bond theory, all these electrons are paired up. No unpaired electrons, right? Molecular orbital theory shows unpaired electrons. So the models are predicting different things. Guess which one is right in this case?
Lewis and valence bond.
No, molecular orbital theory is right. Oxygen is the only is a magnetic liquid. Show you a picture. This is kind of cool. So oxygen, this is liquid oxygen. And if you pour liquid oxygen onto a magnet, it will suspend itself between the poles of the magnet because it's a magnetic liquid. Why? Because it has unpaired electrons. Only molecular orbital theory predicts that out of the three bonding models that we've looked at. And in fact, it's correct, as we can see right here, that the liquid oxygen suspends itself between the poles of a magnet. Okay. All right. Very good. Let's see. What else do I want to say? All right. So let me ask you this question. See if you can get this right. All right. So I'm going to pull you. So it's asking you to find the bond order in B2 minus, right? Here's B, boron, right? How many valence electrons in boron?
Three.
Three,
But
right? Okay, three valence electrons. Here's the energy ordering for boron 2, C2, and N2. So answer me this question. What is the bond order of B2 minus? Now, when you have a minus sign, that's an ion, right? So what do you have to add for a minus sign?
You have to add an electron.
You have to add an extra electron, right? So you have to add an extra electron. So go ahead and draw the MO theory diagram for B2 minus and answer the question, what is the bond order? Okay, 10 more. Try to finish up the next 10 seconds. All right. The right answer is, oops, it's B from current slide B. Sorry, I probably had that on display. Anyway, so the right answer is 3/2. Okay. 3/2. How do you get that? 7 electrons. Let's just put them in, right? We just got to know the order and we just put them in. 1, 2, 3, 4, 5, 6, 7. Right? 7. So the bond order, how many in bonding? How many electrons in bonding?
5.
6.
5
Yeah.
minus how many in anti-bonding?
2.
2 divided by 2. So that's 5 minus 2 is 3 divided by 2, 3/2. Diamagnetic or paramagnetic? Paramagnetic. Correct. Very good. Okay. So, all right. So that's it for that. That's what I want you to be able to do for molecular orbital theory. I know that was a little bit quick, but let's go to the review for the exam. Okay. And then I'll stick around afterwards and answer any more questions you have. Okay. So the exam is going to cover chapters 10 and 11, right? Chapter 10, you got to know the different types of chemical bonds, ionic versus covalent, right? The Lewis model for chemical bonding. Again, a chemical bond is a shared electron pair. Know how to draw ionic Lewis structures and especially know what lattice energy is, right? Remember, lattice energy is the energy that's given off when the gaseous ions form a lattice. And I especially want you to know the dependence of lattice energy on both bond length and on the charges of the ions. How does lattice energy depend on the length of the ionic bond? And how does lattice energy depend on the charge of the ions in the compound? Okay. And then, of course, I want you to be able to draw covalent Lewis structures, right? For any number of molecules that I might give you, right? Then know about electronegativity. What is electronegativity? How do you determine if a bond is polar, right? Know that. Be able to draw resonance structures where you need to. Be able to assign formal charge where you need to. Remember that formal charge is a guide towards writing the best Lewis structure, right? And the lower the formal charge, the better the Lewis structure. All right. Then know the 3 exceptions to the octet rule, right? Odd electron species. When you have a molecule that has an odd number of electrons, usually those molecules aren't stable, but occasionally they are, even though the Lewis structure doesn't have a complete octet on all the atoms, right? Know that beryllium and boron, those 2 elements of the periodic table, tend to form incomplete octets. Beryllium tends to form compounds with only 4 electrons instead of 8 around beryllium, and boron tends to form compounds with only 6 electrons around it instead of 8. Okay. Then know about expanded octets, and remember that expanded octets can only happen in elements that are in period 3 or below. All right, and expanded octets can either be 10 electrons or 12 electrons. And then finally, know about bond energies and bond lengths, right? And know how to calculate delta H from bond energies. All right. All right. Key skills. Be able to write Lewis symbols for elements. That's pretty straightforward. Write and use Lewis symbols to describe and analyze ionic compounds, right? Compare the relative lattice energies of different compounds, right? So know the dependence again on bond length and ionic charge on lattice energy. Calculate the lattice energy of ionic solids. You don't have to do that. All right, so forget that one. I should have crossed that out. I forgot. You will not have to calculate the lattice energies of ionic solids. Be able to classify bonds as pure covalent, polar covalent, or ionic. Be able to write and use Lewis structures to describe and analyze molecular compounds and polyatomic ions, right? So be able to write Lewis structures for these things. Use formal charge to guide you to the best Lewis structure. All right, know how to assign formal charge. Write Lewis structures for molecules and ions that are exceptions to the octet rule. And then finally, use know what bond energy and bond length is. Okay. Key equations and be able to calculate delta H from bond energies in a chemical reaction, right? And the equation for that is right here. Remember, you sum all the delta H's for the bonds broken and the ones for the bonds formed. And remember, breaking bonds is always what? Endothermic, right? Which means that the bonds broken, the delta H's are going to be positive or negative.
Positive.
Positive. Always takes energy to break bonds. Delta H's for bond forms are always going to be negative, right? Always gives off energy when you form bonds, okay? So what else do I want you to know here? Formal charge, right? Take the number of valence electrons and subtract out the number of electrons assigned to that element in the Lewis structure, right? Which is the number of non-bonding electrons plus 1/2 the number of shared electrons. And then just be able to figure out delta H from bonds, okay? Chapter 11. So VSEPR theory and molecular shape, right? So be able to tell the shape of anything based on its Lewis structure, right? Should be able to draw the Lewis structure, figure out the molecular shape. Be able to give me both the electron geometry and the molecular geometry, all right? Once you know the molecular shape, and if you know if the molecule has polar bonds, you should be able to use symmetry considerations to determine if a molecule is polar, right? So you can base its polarity on its structure. right? And then valence bond theory, I want you to be able to draw hybridization and bonding schemes, right? You're going to have some practice of doing that on your homework this week. So be able to draw that, know the difference between sigma and pi bonds, right? Be able to hybridize the right atoms in the right way, and be able to draw those and then identify the bond, the orbitals that are overlapping for each bond that's formed. And then finally, molecular orbital theory, just period 1 and 2 diatomics, that's it. Okay, be able to predict two things, bond order and magnetic properties. All right, key skills from chapter 11. Again, predict the shapes of molecules according to Vesper theory. Make sure you know how lone pairs and electron groups affect molecular shape. Be able to predict the shape of a molecule that has more than one central atom, right? By assigning a geometry to each interior atom. And then predict the polarity of molecular compounds, right? In other words, you've got to determine if it has polar bonds, and then use that information to determine if the molecule as a whole is polar. And then finally, determine the hybridization and bonding scheme of a molecule using valence bond theory. And predict the properties, and by properties, I mean bond order and magnetic properties. Okay. The only equation here really is the equation for bond order. All right. So a little more concentrated exam than what we've had in the past because it's just 2 chapters, right? But there's a good amount of material. But if you study for this, you should be able to do well. All right. All right, so that ends, oops, what happened? Oh yeah, we're good, okay. What happened to my other screen? Oh, there we go. Okay, great. That ends the formal part of my lecture here. I'm happy to take any questions. Let's take a 2 or 3 minute break, and then I'll come back and answer questions. If you don't have any questions, you're free to go. Remember about the exam Wednesday and then the following exam on Monday, right? So you have those 2 exams. In terms of assignments, right? There's just a post-lecture assignment due after today. And there is, sorry, yeah, the exam is Thursday. Thank you, Megan, for correcting me. There's a post-lecture assignment due after today. There's that written assignment that you should do before the test, but of course you won't turn it in, right? And then there's the 2 exams and the final lab this week. We're almost done, folks. Any quick questions that everyone would benefit from before I have you guys take a quick break and then come back for individual questions? Any quick questions that everyone can benefit from? General questions. Jane.
I just had a question on, like, I was reading the textbook chapters and there's like a lot of information on the molecular orbital theory and the valence bond theory. And I was just like wondering how much I need to like go over everything, or do I just need to focus on what we've gone over in like today's lecture?
Only what we've gone over in class.
Okay,
There's
thank
more
you.
information in the textbook for sure, but we're not going to cover it in that much detail. So you only need to know. So all you need to be able to do for molecular orbital theory is basically for period 1 and period 2 diatomics, be able to predict bond order and magnetic properties. All right, that's it. For
Okay.
valence bond theory, pretty much everything that's in the book we've covered in the lecture. I don't think we've left much out.
Yeah, thank you.
Okay, great. Okay, I'm going to officially end class here. I'll stick around for questions, but let's take a little, just a 2 or 3 minute break, and then I'll come back and answer any questions you might have, okay? Thank you, everyone. You guys have all been great. Email me if you need to set up a Zoom meeting with me for any reason. Feel free to do that. By the way, I assign final grades based on a formula, right? So if you look at your grade in Canvas, right, your numerical grade, I assign final grades based on that numerical grade. If it's an 89, it's a B+. If it's a 90, it's an A-. If you end up borderline, like let's say you end up at an 89.9, what do? I just kind of look at your track record. Did you work hard? Did you do your assignments? Were you consistent? Did you have one bad day maybe, right? I'll look at things like that and then make a decision on borderline grades. But pretty much I don't decide grades. You decide your grade based on the formula that I use for grading, okay? And those are the final grades I will assign at the end of the semester. Feel free to email me or anything if you have any questions about that. All right.
Video is still recording, by the way.
Yeah, I know. I'm gonna stop recording here. All right. Thank you.